to all the improvements and changes that have happened over the last decade and a half or so. So what am I going to talk about today? I want to talk about astrophotography. Like many of you, as a youngster, I really was interested in astronomy. And when I neared retirement age, some of my coworkers that had already retired told me that retirement is an opportunity for second childhood. So you can go back to the things that you've always liked in the past. So I felt younger already. And about 12 years ago, I decided I was going to retire and thought, well, it's got to have something to do with astronomy. So I thought, well, okay, how about astrophotography? So tonight I'd like to talk a little bit about the hardware that I've ended up getting. Also about, in general, how I collect the data and how I process the data. Then I'd like to share with you some of the astro images that I've got. It's been a dramatic learning curve. I don't pretend to be an expert yet. I probably will never be an expert, but the journey is where the fun is, not the destination. Like any good hobby, you have to have a helper. And she's very non-judgmental. She never makes fun of me, and she doesn't get upset when I make big mistakes or when I change my mind. And appropriately, her name is Sky. The first thing I wanted to get was, I wanted to get some hardware. So my first astronomy hardware I got was a jackhammer and a cement mixer. And I used the jackhammer to happily dig holes and the cement mixer to happily fill them with concrete. And after a few months of work, I ended up with what I call the Fish Creek Observatory. And it's a 10-foot diameter fiberglass dome. I got it as a kit from Technical Innovations, a company in Maryland at the time. And you can see my helper there kind of supervising to make sure I got it right also. Inside, one of the most important things if you do in astrophotography is the actual mount, because you have to be able to hold the telescope on the target and have it stay there for an extended period of time. And the mount I ended up with, let's see, I must have a pointer somewhere in my pocket probably, is a microphone. Alrighty. This time with feeling. Yeah. Is a software bisque ME2 mounts. Software bisque is in Golden, Colorado, so it's a local company, and it's a very robust system. On top of that, I mounted a research grade CDK-17 telescope, 17 meaning that the primary mirror is 17 inches in diameter. So the light comes in, hits the mirror, comes up to a secondary mirror, comes down through a lens configuration, and comes to a flat focal plane back here on the camera. It's actually an astrograph is the technical term of the telescope. The camera is a Santa Barbara Instrumentation Group, or SBIG camera. It's a large 16 megapixel camera, 36 millimeters by 36 millimeters. If you're familiar with an old 35 millimeter camera, they were about 24 by 35 or 36 millimeters. So this is square. With 16 million pixels, it's a mono camera, so it is only in black and white. And it has electronic cooling, so I cool it down to about 25 degrees below 0 Celsius, which is about minus 13 Fahrenheit, in order to reduce the electronic noise when the shutter is held open for an extended period of time to collect data. In front of that, there's a filter wheel that has 7 positions for 7 filters. I have red, green, and blue filters so that we can have color images coming from the mono camera. I also have 3 other lenses that are which are designed for collecting information from specific physical and chemical changes for hydrogen alpha, sulfur 2, and oxygen 3 transitions that are occurring. In front of that, I have a guide telescope that picks off a little bit of the image from the big scope so the camera can keep centered on a given star, so the mount can be fine-tuned to keep it adjusted. back in the old days, not too many years ago, an astronomer had to tweak the dials, but now the computer can do it for us. And then in front of that, there's a focuser and a rotator to rotate the camera to get it into different positions, different orientations. The overall field of view from the camera is about 1 degree squared. For reference, the full moon is about half a degree. So if you think of 4 full moons, that's about the portion of the sky that this telescope can see. The whole thing is tied together with a computer that's out in the observatory that controls the dome to rotate it to keep things lined up. It controls several features of the telescope to cool it off, and also to remove dew, an anti-dewing system on it. It also controls the focuser and the rotator and the guide camera and the filter wheel and the actual camera. So it all gets tied together. So let's see, hit the right button here. Whoops, wrong button. It took a long learning curve. It's just kind of like drinking water out of a fire hose to get all of those things to work at the same time. But over the years, I've had fun doing that. For several years, I collected data up in Estes Park, which is where I live now. It's where my home is. And I found that even though it's dark up there, there is a lot of turbulence from the air currents as they go over the mountains. You get turbulence, and that affects the stars to where they're, instead of being pinpoint, they're bloated and kind of big, large in diameter. So I finally convinced my wife that wouldn't it be nice if we moved down someplace where it was warmer in the winter? And so Southwest New Mexico was where I ended up going. Ended up moving the whole telescope system down to a place in Southwest New Mexico called the New Mexico Astronomy Village. And I built a new base for the telescope, for the observatory, brought everything else down as it was. I learned about 2 things down there. First of all, I learned about caliche, which I didn't know what it was until I got down there. It's natural concrete that's under the surface. But luckily, I had my jackhammer and my cement mixer, so I was able to jackhammer through the caliche. I also learned about rattlesnakes, so I built a rattlesnake fence all the way around what I call the astronomy complex. I call the place Starbase 13 down there. Several years working with that, and I got to thinking, there's a new technology out for using the mount to observe, to keep things centered. So I ended up getting a different mount, which involved cutting a hole in the concrete base, getting the jackhammer out again, digging more holes, filling them up with concrete, and I ended up with a new mount, which is from Plane Wave Instruments, which is an L500 mount. Instead of having a separate motor, gears, and belt drive, this has just the motors are actually integrated into the axis. So it's a direct drive type thing. Much more accurate pointing capabilities. So the net result is I no longer needed a guide telescope up here, so I simplified the optic train for the camera, and I find that I typically can take 10-minute exposures without having to guide anything. It just is that accurate. So that's very nice, and that's just a technological advance that had come along within the few years that I've been playing in this particular sandbox. I happily used this for many years collecting data, and I'll share some of the pictures with you in a few minutes. But I got to thinking it would really be nice if I could see a bigger field of the sky than just the 1 square degree. So I tried different configurations and ultimately decided that it would make sense to why not just build another observatory, It was so much fun. So what did I do? Well, I got my jackhammer out, and I got my cement mixer out, and I happily dug some more holes in the caliche, and I ended up building this particular observatory. I'll show you more about it later. Notice how I also had spare time to pour extra concrete around, just because, a concrete mixer unused is like, well, what are you doing, Now this one is configured similar to the observatory that's in the museum here in Berthoud. It's a roll-off roof. So it rolls off, and I have room in there for 2 piers, so I could actually have 2 telescopes at the same time. Right now, I only have one in there. That's on a pier. I have others sitting around. But I got a small version of the plane wave direct drive telescope, mount. This is an L350. And I have a wide field telescope here. It's called a Celestron Raz 11, the 11 meaning it's 11 inches in diameter. The other telescope was f6.8. This one is f2.2 if you're familiar with camera nomenclature. The field of view of this one is about 10 square degrees. So think of 40 moons, full moons in an array. So I can see much larger images with this. Now the penalty you pay is you can't see them as deep because you don't have as much resolution. But it's also very fast, so you don't have to collect data for as long. The light comes in, hits a mirror, it goes through a corrector plate first, I should have said, and then hits a mirror, comes back up, and then the camera's mounted right in front of the scope. I have 2 cameras there. One of them is a one-shot color camera, similar to what you would have on a digital camera. The other is a mono camera where it has also filters that I can put into it. This one is a different technology, and it's actually about 63 megapixels. The other one was about 16 megapixels. Most of the things that I will show you were actually taken with a larger telescope. Also, I've only had this one operational for a couple of years. So that was the hardware. So how do we collect the data? And collecting data is both science and technology. You got to first you got to know what is the target that you're looking at and what kind of emissions is it giving you. Obviously, we're looking at light, but what kind of light's coming out of it? And also, of course, the technology is what kind of hardware are you using to collect that data and how do you do it? It's necessary to calibrate a lot of things to get things operational. You have to calibrate the mount to make sure it's pointing where you want it to point, and also that it's tracking at the right speed to offset the Earth's rotation so it stays focused right on the target that you're wanting to look at. You have to calibrate the telescope also because it doesn't perfectly pull the data all out. It's called vignetting, to where further away from the center you might get less light there, so you need to somehow correct for that. And then you also have to do some calibrations of the camera. First of all, recall that I said we cool the cameras down so that the electronic noise isn't as great, but still it has electronic noise. So if you take say a 10-minute exposure, you need to be able to subtract that noise off to try to maximize the signal that you're getting from the target versus the noise or the signal that you're getting from the camera. It also, every time you transfer the data from the camera to a computer, it also introduces noise. Luckily, it's fairly constant, so if you make a calibration curve, you can subtract that off also. And kind of the project, the basis of the approach is you select a target, you stare at it for an extended period of time. I typically have found that down in New Mexico, I try to take a 10-minute exposure, stop it, transfer the data to a computer, and then take another 10-minute exposure, and do that repeatedly. And you might say, well, why don't you just take the long exposure? Well, first of all, you might get so many signals that you exceed the capacity of the camera to store it. Probably a bigger problem, or at least a big problem, an increasingly big problem, is we're getting more and more satellites up with StarX and Starlink and these kind of things. So it's seldom that anymore that I get a sub-exposure that doesn't have at least one satellite trail that goes through it. So if you have multiple subframes, is what we call each of these little sub 10-minute exposures, you can actually get rid of the trail of the satellite, and it doesn't ruin the whole image. We'll talk a bit about that later. So we collect many sub-exposures. My typical rule of thumb is for most targets, I like to get at least 4 hours worth of data for each of the filters, which is as a minimum red, green, and blue. So there's 12 hours right there. And if you do the other specialized scientific filters, which are typically narrow band, which means you don't get quite as much signal per minute of exposure, might have to take more than 4 hours. And it depends on what the target is, which ones you want to collect. Typically, the idea is the technical term is you want to maximize the signal from the target to the overall noise that you're getting from the pieces of electronic equipment that you're using. So you save the data and then you try to transfer that to your computer. Then what do you do with it? Well, you use software to try to convert it into what I call a pretty picture, because that's kind of the goal of this. And it's both science and art. Well, my background's science, and I don't have much background in art, so it's been an extreme learning curve. It takes many, many steps to get what I call a pretty picture. But the whole idea is to tease the data, because the data is there. There's a picture in there, typically. You just have to figure out a way to maximize the signal and minimize the noise. There's software that one can use. I won't bore you with this various specific ones. I might add that software keeps improving. Now, a bigger factor probably in my case is I've been going through this very steep learning curve. So I've learned more and more about how to actually get better pictures. In fact, I am finding that just about every year I could go back and reprocess the data that I collected way back from the beginning and get a better picture. So in some respects, you might say, why not just stop collecting the data and just keep reprocessing it? Well, I find that gets boring. And also I find that the overall sum total of the sport, if you will, of astrophotography is collecting the data, playing with the hardware, and then playing with the data. And in my case, I even go along, and in many cases, I actually go ahead and print the data out into a picture. I have typically printed 17-inch by 17-inch photos for the square shots. And for the RASA, the wide field one, which has a different shape, I usually go 17 by 22-inch prints on that. So I've had other people, kind of talk with me, well, what does it kind of look like when you're doing a picture? You just go out and you just go snap, or do you just open it up and you get a picture? So let me show you a few pictures along the way to give you just a little flavor for where this data comes from. This is a picture of the Vulture Head Nebula. Do you see it there? Looks pretty nice, doesn't it? Wait a minute, I don't see anything. It's supposed to be a reflection nebula. Well, first of all, this is an unstretched, I'll explain what that means in a second, image. Keep in mind that the stars, the real bright stars, you can kind of see them there. But the things that we're trying to look at are really, really faint. These faint, fuzzy objects is the targets that we're trying to find. So sky value, just a blank sky with nothing has a certain amount of brightness. Luckily down in New Mexico, it's not much, but it still is there. So if you can take the images that are, the pixels that have the data in them that are there, just barely above that, if you make that a lot brighter, and meanwhile, if you go clear up to the top where the image pixels are bright, don't do anything to them. And in between, you kind of do it in between. You kind of call it a non-linear stretch, to where you stretch to make the dim stuff brighter, and the real bright stuff you leave alone. So if you do that, you come up with what is called a non-linear stretch. Now, keep in mind this. Say that again?
Very nice.
Very nice. I forgot to say something, by the way, before we started. Please feel free to ask questions along the way. Don't hold them to the end. Please pop in anytime you have a question. So, wow, that's a beautiful picture there now, isn't it? Well, wait a minute. You see it? What do you think of that? Once again, this is one 10-minute exposure. In this particular case, I ended up taking a total of 48 10-minute exposures, about the same number of red ones, green ones, and blue ones. So I went through each of those exposures. I did all the calibration for the color. I did the calibrations for the vignetting from the scope. And then I combined them, and I got that. So now we're starting to see something. I can maybe even see a vulture head there, or a baby nebula. But there's still a lot more data in there if you go and you spend the time and the effort to try to tease the information out of it. So what I've done is I've done a lot of different steps. One of the things that you can do is since these stars are known, we know what the spectra of them are. You can go into the different stars and figure out what color should they be, so you can correct the color of the actual image that you got here. So in this next one, I removed the stars and I did a lot of processing on it. And suddenly it starts looking like an image. And just for information, this particular object is about 400 light years away. And I'll tell you what a light year is in just a few minutes. And it's about 25 minutes by 30 minutes. In other words, it's about the size of the full moon, except you can't see it, but it's there. And if you really want to be a purist, you put the stars back in. I want to share 2 more little images for you before we go looking at some final products. When I was in Estes Park, when I first started running it, I took lots of pictures every night, and I had a lot of fun doing it, and I was just scurrying around collecting all kinds of images. This particular one is M81, sometimes called Bode's Galaxy. And if you look at it, you can certainly see that it's a galaxy. It looks kind of like a spiral galaxy. And in this particular case, I did it way back in 10 years ago, I guess, and exposure of about 4.6 hours. Well, after I moved the whole rig down to New Mexico, and I admit this is not a good scientific experiment because I changed several variables at the same time. Not only did I change its location, but I also ended up taking a slightly longer exposure, and probably more importantly, I also was further along my learning curve on how to process data, and I got that. Now that's back in 2019. Kind of remember that image, if you will, because we'll see M81 again, maybe a couple more times this evening. But that's where it was there. In that particular case, I'd taken 10.8 hours worth of data. And you can see the data, the information that you can tease out of it is at least I find it fascinating. So why don't we look at some nebulae, which are basically just clouds of gas and dust. Whoa, we went too far. Sorry, whoa. Did you catch all of those? Okay, here's one of the more iconic images that one can have, Horsehead Nebula. On this one, let me explain what I've got on the left so you can kind of, because I'm going to have this kind of information on all of them that were coming along. I typically maybe give a popular name to it, maybe a more scientific name to it, and I like to typically show the distance and also what constellation it's in. In this case, it's 1.4 thousand light years. And I suspect most of you know what a light year is, but let's go over it just to be sure. A light year is how far light can travel in 1 year. It's a measure of distance, not time. Light can go around 186,000 miles per second. So light from the moon takes about 1.5 seconds. Light from the sun takes a little over 8 minutes to get to us. Light from the next closest star is around 4 years to get to us. So that would be called 4 light years. If you take 186,000 miles per second and multiply it by the number of seconds in a year, you get around 6 trillion miles. That's 6 with 12 zeros. So it's a large unit of measure, but since the distances are so large in astronomy, it's a useful unit to use so we can compare things. If I put a K, it's 1,000. If I put an M, it's 1,000,000 in front of the LW. And the size of the diameter of the actual unit here is about 7 light years. So if you think about that, that's like 7 times 6, 1,000, trillion miles. That's what I'm trying to say. Yeah, thanks. Now, what does it look like in the sky? What is the angular size of it in the sky? We use terms like degree. We said the moon was about 1/2 degree. And then there's 60 minutes in a degree and 60 seconds in a minute. This particular thing is about 8 minutes by 6 minutes. So that unit, that little object there is much smaller than the full moon, which would be about 30 minutes. So I usually think in terms of the moon to get myself calibrated as to how big is this object looking in the sky. I oftentimes give a little description of what it is in terms of what kind of things happen to let us see that, where maybe it's getting a star. Talks about this reflection nebula, for example. I just for interest, I say how many hours exposure I have that I've incorporated into the image also. In this case, 15 hours. And I put a date down, not because the object has changed in that length of time, but my skill set has got better. The software's got better, and more importantly, maybe I've got a little better in processing it. So that kind of gets it calibrated as we walk along my my second childhood here in my retirement hobby. Yes?
That's exposure time. How long is processing time? How long is that?
Well, it depends also on my experience base. Probably on that one, because that was done quite a while ago. As a rule of thumb back then, at least as long as the exposure time. And that part of that's because, I'm learning. I mean, it's a steep learning curve. And of course, that's part of the fun of it. Of course, that's the excitement of it, is to go in and to find yourself creating something, to know that object's up there. I mean, you look at it, of course, you can't see it with the naked eye, and with a good telescope, you might see something a little fuzzy, but you're not going to see that kind of detail. Well, with that preamble, you'll be able to look over on the side and read about the object there. And once again, yes?
15 hours.
Yes.
Was that all done in one?
No, excellent question. I should have covered it. Beautiful question. It definitely first wouldn't be all at the same time because the nights aren't that long. Secondly, the further up in the sky you are, the less atmosphere you have to look through. So if you get down real low to the horizon, you're looking through a lot of atmosphere, and that blurs things out. So you kind of want to find a sweet spot when it's fairly high in the horizon. I mean, above the horizon, towards the ecliptic, towards the center of the sky. And you can do it over different days, depending on the object, different months, and in some cases, different years. I have some images I've collected data over multiple years, and with proper alignment, you tweak it around and you twist it back and forth, then you can combine them. But good question. Yes?
You said 15 hours, but you're shooting in narrowband, so 15 hours total?
15 hours total, each of them nominally a 10-minute exposure. So 6 times 15 would be the number, 90 subframes or so that I use to process the data.
There's a gentleman right here.
Yes.
So I have a question from like a while back. So when you
Okay.
When you had the picture up, when you talk about how you built put the telescope together.
Yes.
Kind of like the calibration.
Yes.
So once you calibrate it, is it set, or do you need it like when you need to calibrate it again each time something changes?
Well, that's one of the beautiful things about having an observatory. I learned with my years of experience here at LTO that it's so nice to have your telescope set up every time, and you don't have to take it out into the yard and recalibrate it. Now, in time, it might shift around, but basically you do what's called polar alignment, where you find out exactly where the North Star is, which gets you close to the rotation point. It's not quite perfect, but it's close to get you started, and you keep tweaking it until you get it aligned properly. So that's one calibration that you would do on the mount. On the telescope, there's several calibrations you would do. You make sure the optics are all aligned properly. And also you want to find out how much data are you losing because it doesn't bring it all to focus at the same time. Also, when you do what's called a flat field, that's what that particular calibration is called, you're looking for dust that might be getting in the optics. And by having it there, you can remove it essentially from your target image, the image of interest. It's and believe me, in the desert, I know it's shocking, but you actually do have some dust that's blowing around. Did I have other questions?
Good.
There's a little question. What's a question? I didn't catch that. Well, it can certainly be a seahorse. Yes, it could be. It kind of looks like one to me. Yeah, that looks like a seahorse. Yeah. Yeah, that's good observation. Yeah, very nice. If no other questions, we'll go to the next image. You've probably all heard of Orion's Nebula, M42, if you've been here lucky enough to look. It's hard to see, but it's actually the trapezium is 4 stars right in here area. This particular is about 65 by 60, so it's about 1 degree squared. As it turns out, this is a bigger image than I can see with my big telescope. So this is where I'm using the wide field telescope in the Roloff Observatory. So that's when I say the RASA, that's the kind of telescope that it is. You can see how far away it is. It's pretty close, actually. It's 1,344 light years away. It's about 24 light years in diameter, and it's a place where stars are being formed. And it's a large area, and it's close. And I collected the data just this year with the RASA telescope. It's a very difficult image to process, maybe, because it has such a dynamic range of color and brightness in it. So it was a challenge, and I'm sure I should spend more time on it to make it a little better. But I wanted to share what I had. This is M1. Now, let me explain. M stands for Messier object. Charles Messier in the 1700s was a comet hunter. And back then, they would see a fuzzy object, and if he was lucky, it would move and be a comet. But he started seeing all these objects that were fuzzy, but they wouldn't move like a respectable comet would. So he made a list of things not to look at. And he ended up with some coworkers to help him along of 110 items not to look at. In fact, there's a chart of them back there. With today's modern telescopes and cameras, you end up with pretty fancy things to look at. This particular one was the first one he put on his list. It's extra interesting because back in 1054, Chinese astronomers saw a guest star, a new star, which now we know was a supernova, a star that had blown up. And after less than 1,000 years, it's 11 light years across the debris cloud. And if you look at the intricate detail there, it's kind of interesting. I might note that this is a short exposure, and it was done way back in 2019. I will confess that I have collected a lot more data on it now. I just haven't processed it, so I can't share it with you yet. But I find that one interesting. It has historical reasons. It's the only one that we actually have seen blow up where we can actually see the debris cloud that came from it. So it's a nice one. Another interesting one is the Eagle Nebula. You kind of look at that and it sort of looks like an eagle. It's also pretty close, 5,700 light years away. You can look at it. It's slightly larger than the full moon. It's a Mission Nebula. Perhaps you recognize sort of the image because it was the Pillars of Creation, one of the earlier targets that the Hubble telescope took. And if you just zoom in on it, there's kind of the Pillars of Creation. So it's kind of neat to at least recognize it. This particular one, I collected the data back in 2019. You can see it had a fair amount of data. And I reprocessed it this year to get that. So that's probably about as good as I can do on that one right now. Next year, maybe better. I also collected data in the narrowband on this particular topic, or target.
Oh, nice.
And that is the same, it's called the Hubble palette, which uses sulfur, hydrogen, and oxygen, which happen to be 3 of the narrowband filters I have, where sulfur is red, green is hydrogen, and oxygen is blue. And that one looks maybe more like what you're familiar with looking at the Hubble. Yes?
Are those diffraction spikes from the telescope, or do you have them in?
No, see, there are diffraction spikes. It's a reflector. It has, the secondary mirror has. Yeah. This is on the, it's on, if it's on the wide field one, it's going to say RASA exposure. This one is, almost 16 hours. Once again, data collected in 2019, reprocessed this year. But I'm not a big fan of nebulae, but I like this one. Another one that's a lot of people look at through their telescopes is Thor's helmet. It's kind of an interesting configuration there. You can see, read the details about it. It's quite a bit smaller than the full moon. I reprocessed it 2 years ago, and And you can see about 14 hours worth of data. Okay, let's look at another one. This one's a kind of, it's interesting that it's three kinds of nebula kind of put together, the trifid, the tri. I did it a long time ago, 5 years ago. There's not much detail there, but I find the colors of the images interesting. You can see it.
Question.
Yes.
Do you set this up for 5.5 hours of exposure and then go in the house and go to sleep? And it turns off automatically?
Maybe. Yes. I have now got my system automated enough to where I have controlling software that controls the computer, that controls all the pieces of the astronomical equipment. So I tell it what I want to look at, and it knows where to go find it. I know how long I want it to look at it there, and that depends on how, when it's in a sweet spot in the sky, so I pick several targets that it can go by. And also I have it, since in the desert in particular, when it cools off at night, you have dramatic temperature changes, so the focus shifts around. So it will automatically refocus. I also have I guess I have a weather station devoted to this that's making sure that the wind doesn't come up and get too high, or heaven forbid, it doesn't rain. In the desert, it didn't rain that much. Up in Estes Park, I had to worry about snow and wind for sure. So it monitors it, and if it gets above a certain level, it shuts everything down, closes the dome, and doesn't let it, hopefully, rain or snow on my telescope. So yes, I have it automated. So the next morning, in midnight, I have to admit, I don't really sleep as well when I got it running, because I wake up in the night, or my assistant Sky wakes me up and says, hey, go look and make sure everything's okay. So I'll go in and look at the computer and make sure everything's happy, and if it is, then I go back to sleep. So yeah, that's a great question. I should have mentioned that earlier, but that's.
So if you've got like only 6 hours of sweet spot, and you want to get 18 hours or 15 hours of exposure, then you can do it 3 nights in a row, and you pretty much just tell it what you want to look at then.
Yeah, it knows where to find it on a given night, and it's it doesn't have to be consecutive nights. It could be separate months. It could even be different years.
Oh, wow.
So you can, now admittedly other things are rotating, but the software is smart enough to get it realigned back up, and then stacks them to make sure that they're all properly aligned. And you go through and you throw away some data that's not so good. I referenced it. I'll talk about it a bit right now. After you stack them all up, you have, like in a big telescope, you have 16 million stovepipes here of data, pixel by pixel by pixel by pixel by pixel, and here comes a satellite through, zoom, and that particular pixel where the satellite went is brighter than the other, say 24 in that stack. So you put the appropriate statistical parameters in place, and it throws it away. Now a satellite track through an image out of the 16 million pixels, it's only going to be a few hundred pixels that you throw away. So you didn't really lose that much of the data, but if you don't remove it, the picture's ruined.
Right.
So you can do all of those things anymore with software, and the more sophisticated the software is getting with time, makes it easier and easier to pull that off. I mean, it's almost criminal how easy it is now compared with the people that did it back when it was with film cameras and they couldn't do any of those kind of things. Now, admittedly, they didn't have Starlink satellites to dodge either, but that's a different story. So anyway, I find that a colorful image, not particularly exciting. This one is an emission nebula. It's called a crescent. If you look at it through a telescope, all you really see is this part of it. You don't really see all the rest of this. I would call it maybe a brain or something if I were naming it this way. It's an emission nebula, once again done way back in 19, and not that many hours, and it's quite a bit smaller than the full moon. Yes?
So with a 7.2 hours of exposure, how much data is that? Like gigabytes?
Well, each subframe is about 32 megabytes. But to do the processing on it, you do you do dozens and dozens and dozens of those in different stages of the calculation. So it requires a lot of computer processing power to pull this off. I mean, it's, about 3 years ago, I got a fire-breathing Threadripper telescope with large amount of memory, really fast graphical processing unit, and I used that, which was so much better, and it cut down. They have a benchmark built within the software that I use, and it reduced the amount of time by about a factor of 10. Now, the technology moves on, because just this spring I bought a laptop, the best laptop that Dell makes, and it can actually do it as well as the fire-breathing one 3 years earlier. So technology keeps moving on.
So do you end up having like hundreds of hard drives laying around with all the data on it?
Well, anymore, a hard drive can hold a lot of data, but I have, I think, around, 75, 100 terabytes of hard drive hung on the big computer, and most of them are full. So you collect a lot of data over time, especially with the secondary, the big field rasoscope, because it's got 63 megapixels per shot. So yeah, it's intensive with the graphical, with the processing requirements. Yeah. Yes.
Do the telescopes that are in orbit, do they require the same type of processing, or is a lot of the static stuff already gone?
I think they probably require similar calibrations and processing, yes. Keep in mind that the Hubble is not really doing it in red, green, and blue. The colors that you see there are synthetic colors, similar to the one that I had on what I call the Hubble palette, the sulfur, hydrogen, and oxygen. But yeah, there's professionals that get in there and do that, and there's a lot of amateurs that can get that data and play with it also. And frankly, sometimes the amateurs might do as good a job as the professionals, but that's kind of the name of the game anymore. It's the technology for these kinds of things is getting such that an average amateur, an old retired amateur like me, can get images better than the professionals could do 50 years ago. It's just, and it's not that I'm so good, it's just that the technology has moved that fast, including the software. The Jellyfish Nebula is actually a supernova remnant. It's bigger than the full moon. You see, it's about 5,000 light years away, so it's relatively close, astronomically speaking. 70 light years across. Large uncertainty as to how far away it is. This was back in 2019 when I collected the data and did the processing. Yes, I should go reprocess it again, but I haven't. But I still find it very interesting. The next one that I'm going to show you is actually done with a narrowband filter, where I had hydrogen, sulfur, and sulfur. So hydrogen was red, green and blue were sulfur, and I liked the additional detail that popped out on that, on these little striations that are going out. It does indeed look like a jellyfish to me. A bubble nebula, once again, an old image, but it's kind of interesting. It's a long exposure, 21 hours. It's actually a hot stars with a stellar winds blowing that big bubble, and that's a big bubble. And I know we can see it through the scope here, but it's an interesting one. You can see the size much smaller than the full moon.
So,
well, I'm sorry.
how many bands do you collect?
I have 7 filters.
7 bands.
Yeah, I can, but I don't always do it. It depends on what's happening in the, if there's no hydrogen alpha or sulfur or oxygen, I don't do it. When I first started doing processing, the mode of operation typically was to have a luminance band, which was basically all the colors, and then a red, green, and blue, and then you combine them. Well, most people now have gone away from the luminous band and take the extra time and put it on red, green, and blue. And that's the way most cameras work anyway.
You don't do infrared?
I do not do infrared, that is correct, I do not. I'm down in the atmosphere here, I do not do that, no. So everything is visible light. Here's the, how did I get there? I guess okay, there's the bubble. Here we come from the bubble. I know one of the favorites to look through here in the summer is the Ring Nebula, the donut galaxy. I used to like back in the day when, this was years ago, but Homer Simpson's galaxy, because he liked donuts. If you look at it, one of the other volunteers and I, after the groups had left, spent hours trying to see the center star. We never could see it. And it's partly our eyes. It's a great scope. Partly it's the viewing conditions. But it pops right out with when you're taking an image. But look at this outer band way out here, which you certainly can't see visually. So it's a real interesting one. What this is, it's called a planetary nebula. As a star nears the end of its life, it starts puffing out matter. It's not just its atmosphere, but its actual material of it is puffing out. By the way, our star's going to do that too. The sun's going to do that in a few billion years. So, you might keep an eye on that, see if you see that happen. But they look like a planet. They have nothing to do with a planet, but in the earlier telescopes, they look like a planet. So that's what they are. And they're kind of pretty. They're kind of interesting to look at. This is a long exposure. I did it 4 years ago, so I probably ought to go back and see if I can't tease a little more detail out of that. You can see it's very small, 3.8 minutes. So interesting. I know, if you've been here before, I'm sure you may have looked at it through the telescope. This is another planetary nebula. The image, I don't know, I just like the color of it. It's called Headphone Nebula, which I can maybe make it be that. But it's a long exposure, processed a long time ago, but it's another center star that's puffing out its atmosphere as it nears the end of its life. Interesting colors. Here's maybe my favorite planetary nebula. It's pretty small. If you look at it, these are seconds, so it's less than a minute by a minute. And oh, I'm sorry.
I think she's just screwing around.
No.
Really?
Okay, speak up if you have a question, because there's no bad questions. So if you have a question, I'd be happy to try and answer it. Okay. Yes?
On the previous image you just dismissed, are those galaxies I'm seeing in that part, or was it curiosity?
I think they're probably galaxies, but I can't guarantee it. It's not that good an image. Probably I shouldn't have put it in. I just like the colors. But that's a good question. We'll see some coming up where you're going to see all kinds of background galaxies, and I suspect they are, or they may be uh-ohs when I was processing. I can't vouch it. I can claim that I was in my learning curve. Trouble is, I'm still in my learning curve. So. Anyway, we used to be called the Eskimo Galaxy. I'm not sure that's politically correct to call it that way anymore, but boy, I can sure make that be a face and its fur coat being around it. Clown face, that's a good one too. I find that one interesting. It's surprising the amount of detail that kind of pops out from that image. Another one that I actually just did on a whim, it's very small. It almost looks like a star, but it's such a bright star. And one of my visual astronomer friends down in the New Mexico Astronomy Village asked me if I would just go ahead and take a picture of it so he could kind of see what it looked like. And I said, well, okay. So I gave him almost 4 hours a day. I didn't think it was worth more than that. But you can see that it kind of looks like it's called the ghost of Jupiter, because, if you don't know what you're looking at, you might say, well, hey, that kind of looks like Jupiter. Anyway, it's a very small, 25 seconds, half of a minute. Let's look at some stars and galaxies. I'm going to start off with a picture I've taken, or two pictures I've taken without my telescope. During the last year, we've had two solar eclipses that occurred. One that I observed in a cemetery in Hobbs, New Mexico. And then 6 months later, I went to a town in Gatesville, Texas, close to Austin, and on a small ranch, and took that picture. And they look quite different, but yet they're both eclipses. So the whole idea of a solar eclipse is just a happy coincidence because the sun is 400 times larger than the moon in diameter, but it's 400 times further away. So both of them look like they're about a half a degree or 30 minutes in size. And there are several parameters involved here, but the main one is the moon's in an elliptical orbit around the Earth. And if it happens to be at apogee when it's further away from the Earth, it's not big enough to cover the sun. So you have the moon's shadow here, but the sun still is shining around it. And by the way, in both of these, I was right on the center line. Why else would I go to a cemetery to take a picture, you know? But if it's in perigee, when it's closest, then it's just the right sized. It depends upon other parameters, but in this case, it was close to the right size, and it just covered up the surface of the sun, and the corona, the atmosphere of the sun, was kind of bleeding around. And you'll notice that there's prominences sticking out that at those red spots that were bigger than what the moon's shadow was. And to kind of help yourself think of the scale of even the sun, which is kind of a small star, these prominences are probably 4 or 5 times the diameter of the Earth. So that was kind of neat. Just a digital camera on a tripod. Didn't need any fancy telescope for this. Didn't need an observatory. I beg pardon?
How much viewing time did you get in the solar?
I think this one, 4 minutes or so. It was, you know, it was modest, but it was appropriate.
Austin wasn't getting that much, getting a lot of cloud.
We were lucky. We actually were lucky for you know, you could see the clouds. You say, oh no, here comes the clouds. And then they magically, well, of course, you know, I was in a small group on a ranch and we were trying to blow the clouds away. And I guess it worked because we got quite a few shots. I was shooting every 2 seconds those. And I lost a few along the way. But it was good enough to where I was pleased with the results. I got the diamond ring. I'm not showing it here, but I got both of them on each end. So it worked out pretty nice to where just where the sun was starting to peak around the moon and it suddenly lights up, looks like a diamond ring, a ring with a big diamond on it. So it's neat also. So I put this one in. I realized it's not really astrophotography, but it is a star.
On those prominences, did you add the red color to make them stand out before?
I intensified them, but they're real color. It was real color. I was shooting it with a one-shot color. Once again, a digital camera, just a big one-shot color camera and of course through a telephoto lens. But no, I didn't. No, that's the color. That's the color they are. Now it's really solar flares that are just on the rim of the sun that's shooting out. But still, they're kind of neat. Now, what I really should have had or wished I had, but don't have, would be a hydrogen alpha telescope designed specifically for the sun. But this is what I had, and it was fun. I had to share it. Let's look at what are we looking at? The Pleiades, M45. I know you've all seen that in the sky. The Seven Sisters, the Subaru. It's really close. The overall size of this was about 40 light years. The angular size is 2 degrees, so it's big. This was shot with the wide field telescope. Short focal time. The actual stars weren't born in this nebula. They seem to be just passing through it, but they're creating really nice, through the dust cloud. So they're creating real nice blue things. It's a real simple image, but I find it intriguing. In fact, I use it as a screensaver on some of my telescopes because I just like the color and it's just, I don't know, it's just fun. And I have to admit, there's some also about an image that I've been able to collect myself. It seems to have a little bit more meaning than if I just see it in a book, you know. M13, a big globular cluster, which are old groups of stars, in this case, that are in orbit around the Milky Way. I think the Milky Way has around 100 or so. The number keeps changing with time, but around 100. And there's maybe 500,000 stars in it. And the neat thing that I find is those stars are about 100 times closer than they are in the Milky Way. Can you imagine going out into the night sky, looking up, instead of seeing 3,000 stars, you see not 30,000, but 300,000 stars? Now, it would really make life difficult for a hobbyist like me trying to do astrophotography with that much light coming down. Short focal length, collected it back in 2019, reprocessed it this year, and you can look way down in there. I put in there the fact that it's a population 2, which means they're low metal stars. We get our elements from the stars that cook them up to iron, and then they blow up as a nova. That disperses out into the galactic clouds, and they recondense again, and they cook some more. So the actual heavier metals are cooked inside of stars through nuclear fusion and other processes when the star blows up. And these were done early, so they don't have much metal. So we know those are real old stars. They haven't gone through multiple things. Our Earth and the Sun, for example, have gone through multiple supernovas to build up the metals or the elements that we see, and that make us all up. We're all made up of star stuff, or nuclear debris, if you don't want to be quite so poetic. But I prefer to say star stuff. Andromeda Galaxy took it last year, once again with the Wide Field Telescope. It has maybe 4 or 5 times as many globular clusters as the Milky Way. Back in the day when I was kind of in school, we know it's bigger in diameter, and we thought the Milky Way, the Andromeda was a lot bigger than the Milky Way, but now I guess there's data coming out that maybe they're about the same size in number of stars and mass. This is just a little bit more diffuse. Notice that there's a couple satellite galaxies going around also, which of course the Milky Way has those too, but can't take a picture of those. So you can see that with the naked eye, and I know you can see it through the scope up there, but I don't think you see quite that much detail. Questions? We'll go through a whole bunch. Remember M81? We looked at it both in Estes Park and also early on. Well, here's a later version that I took. I collected data from 2019 and 2020, total of 30 hours, and reprocessed it last year, and even more details popped out there. It has a galaxy real close to it, surprisingly called M82 by happenstance, I think. But it's kind of a pretty one, sometimes called the cigar galaxy or the exploding cigar galaxy. It has a galactic wind blowing basically hydrogen, this is hydrogen gas basically coming out of it, if you will. Look at the exposure time on that, 69 hours. So this is one of my deeper images I've taken. 2020 and 2023, reprocessed in 23. It's, and it's fairly small. See, it's only 37,000 light years in diameter. The Milky Way is about 100,000 light years. M81's close to 100,000. And then I took it with the wide field just to see where they are in the sky with respect to each other. And there they are. There's M81, there's M82. And look at the separation. The angular separation is about the size of a full moon you could stick in there. And if you look in terms of the diameter, you say, well, what is that? Maybe 200,000 light years apart or so. Pretty darn close. Yes?
Are there any photography methods that would help with depth of field to really see how close they are together? Or just
there are ways to find it out, but you can't really do it with photography. You can look at things like the redshift with the expanding universe, the galaxies. If they're further apart, they have a different redshift, they're not really side by side. They may look like they're side by side, but maybe it just happened to be lined up. Or they may be actually hooked together. In this case, it's a little easier because you're actually getting some gravitational interactions. Those are gravitationally bound. If you remember on M82, it said it's forming its stars at a high rate. You could have read it, I didn't really say it, but you see it's called a starburst galaxy. So it's about 10 times the star formation. And that's because it's gravitationally being perturbed and pulled together to make it react, make the gases come together and start fusion. But that's what they look like together. So, it's a different perspective. You can see there's not nearly as much detail, but it's kind of neat to see them in conjunction with each other. Notice there's another galaxy that kind of popped up there that's fair-sized. A pinwheel galaxy, It's large. Look how large that thing is. It's, 170,000 light years across versus about 100 for the Milky Way. It's about 21 million light years away. Face on. You can see couple years of data, quite a few hours. It's a typical face on. Notice how it's perturbed also. So I don't really know the story off the top of my head, but obviously there's another galaxy either now or in the past that has disturbed that and pulled these stars and gas and pulled it apart. This is another small galaxy, relatively small, that's close to us. It's in the local group. You can see it's about 3.2 million light years away, about the same distance away as Andromeda. And in fact, when Andromeda collides with the Milky Way, this one is also, so it's going to be at least 3 of them coming together. They're all coming at the same direction. Now it's 4 or 5 billion light years away, 4 or 5 billion years away. And I don't know whether your iPhone goes out that far or not, but if it does, put it on your calendar and be sure to look at it. Notice that there's numerous red areas. These are hydrogen alpha areas where it's star formation. They're young, bright, hot stars, and they're active. They're exciting the hydrogen and causing the transition called the hydrogen alpha transition, which is this kind of orangey red color. Another interesting one called the Sombrero Galaxy. Not even too sure. Some literature tells me it's spiral, some say it's elliptical, but it's got this predominant ring around, and it does kind of look like a sombrero. So anyway, a couple years worth of data there from, actually look how far apart the years are there. So, you can grab data, and as long as it's with the same system, you can probably make them hook together.
Got a question.
Oh, yeah, sorry, yes.
That bright halo, sorry.
Yes.
Is that legacy stars or is that an artifact of Earth?
No, that's real. That's stars and radiation out there. Yeah, it really is. It is that bright. That's the reason they say, well, is it a spiral or is it an elliptical? Elliptical being kind of egg-shaped or spherical, without the spiral, and it's got the dust laying here. So you say, well, maybe it's a spiral. But then, wait a minute, no, it must be an elliptical. So it's kind of I don't know what it really is, but. Say that again?
Hubble images look almost identical to that. So
Oh yeah, that's real. I know it's not an artifact of. It's not that I haven't messed up occasionally and create an artifact and say, whoa, look at this, and then, wait a minute, it's me. But my dog Sky never complains. So. Sunflower Galaxy kind of looks like a sunflower. Once again, data collected back in 2019. I pre-processed it last year. A lot of detail pops in there. Interesting. 29 million light years away, so it's quite a ways off. Yes?
When you're reprocessing, are you adding newer data that you collected?
If I do, I say the new date also. In this case, I took the data from 2019 and I processed it from scratch with better software, better experience, maybe a better technique, and maybe even a better idea. See, once you get into this, you're talking art also. Remember I said processing data is science and art, so maybe I have a better idea of what I'm trying to tease out of it. The data was there all along, and I'm sure there's still data to be found if I were willing to go hunt it. Interesting. This one particularly probably has a big black hole in the middle of it, but almost all galaxies we're looking at are having large black holes in the middle, including ours. So that's not totally atypical, other than this one maybe is larger than normal. We'll look at one here in a minute that has a great big one. Anyway, I find that one interesting. 65 million light years away. So notice we're getting further and further away now as we're getting into these galaxies. And by definition, the resolution has to go down a little bit because it's so far away. There's not that much light coming in. Here's a couple of the Messier objects that are kind of interesting. This one has some interesting spiral arms that I found that I liked. So I took that picture. Notice it's pretty small. The moon would be 30 by 30, by the way. And there's M96, its sister, if you will, and it's gravitationally bound to M95, and it's about the size of the Milky Way, if you look about in diameter, but it's asymmetrical. Look how it's just kind of offset, and part of that's probably due to the gravitational attraction of M95. And what do they look like in the sky together? Well, I took it with my wide field, and that's where they are, and you can kind of see that they're 42, so it's much more than a full moon apart. And of course, if you look at the diameters of them, so they're further apart, but still they're gravitationally bound. So it's kind of interesting. I find it interesting. Yes?
Do these photos show the how that gravitational bounding is happening? Like, can you prove that through this image, or is that through somebody else's data?
Well, I'd probably have a hard time proving it with my data. You can certainly see effects of it because you see an asymmetrical galaxy to where it's all distorted, and that's being done by gravity. But I mean, based on my images here by themselves, they would not give you evidence to prove it, but you can see evidence of it. Good question, by the way. So there they are in the sky together. Let's see, I think I know what one's next. Nope, I didn't. This is a Nautilus one. I found it. Now that one's obviously also distorted by something. Some gravitational interaction has occurred to pull that one arm way out. It's a pretty good sized diameter one, by the way. Of course, part of it's the fact that it's elongated. And it's 130 million light years away. That's, that's more than around the block. Another spiral galaxy. I find spiral galaxies interesting. I mean, they're almost all look different. Another one. Black eye one.
There's a question.
Oh, I'm sorry. Yes.
Some of these galaxies are so much further away. Why is your exposure time under 15 hours and some of the earlier ones were 69? I think.
Yeah, well, I'm trying to tease out probably more detail on the ones that are closer. And perhaps, yeah, if I took a longer exposure of this, I could get more detail. But, it's almost a point of diminishing returns if it's too far away. My telescope's only 17 inches in diameter. I mean, that's not small, but these are, this particular one's not too far away, but also it's not overly large either. So it's about half the size, but admittedly, it's not nearly as far away as some of the ones we've looked at. So it's a good question, and I don't know, maybe I lose interest in it. Maybe I say, okay, good enough, let's move on, let's try to find something else. I don't have a good answer. It's a hobby. I don't have to justify it. And as I've said, Sky, my dog, never questions me. So this one, I took it. It's a definite elliptical supergiant galaxy. I did not expect to get any information from it, and I was not disappointed. There's not much information there. The reason I took it is because it's the one where the big black hole was taken. And it's a monstrous black hole taken way back in 2019, and I just had to take an image of the same thing because I could. And it's kind of fun, but it doesn't show anything. If you look at some of the data about the big black hole, it's truly phenomenal. It's a big one. And of course, if you've had a chance to look at the image that was actually taken, that is really, really interesting. I don't know if you're getting hungry, but I kind of am. A hamburger galaxy, kind of looks like a hamburger. Interesting way it turns out. It's got this band of dust that makes it look, some would say, looks like a hamburger. Way back in 2018, I did it. We'll see it again, by the way. If you look at a spiral galaxy on edge, you kind of get a needle. If you look at it this way, maybe it looks like maybe a knife edge or something. Different galaxies, of course. Maybe you can call it a surfboard even. Some people have pretty vivid imaginations the way they name these galaxies. And you have a loony galaxy, which is kind of an irregular one. Probably two merged galaxies that get pretty compacted, merged. Let's look at some groups of galaxies real fast. We're getting kind of late here, probably going over. Am I doing okay on time?
About an hour and a half.
Oh no, not an hour and a half.
Good tonight.
Oh my God. Okay, we'll go fast. Here's one I took in Estes Park. I call it the Estes Park Deep Field after the Hubble Deep Field. And you can see many, many galaxies if you get a good monitor and look at them. A couple years worth of data. We'll go fast. Here's 3 galaxies together in a configuration with the with the RASA telescope. Here's another grouping of galaxies. Small galaxies. This one's with the CDK telescope. Here's a chain of galaxies that's kind of neat to look at. Here's an iconic one, M51 Whirlpool galaxy. The small galaxy, some models would say it's swung by a couple times as they're in the process of merging. The model maybe it's 2 times, maybe 1 time, maybe more. But it's interesting, it's iconic, and it's close enough you can actually get a fair amount of detail. Another one looks like antenna. They're merging. You can see the 2 galaxies merging. Look at the tidal tail of gas and stars that's being thrown out as they're being pulled together gravitationally. About a billion years ago or so, they were 2 separate galaxies. A couple galaxies in the early stage of merging, they kind of look maybe like a butterfly through a telescope. Some more interacting galaxies. I call them galactic train wrecks. They're fun to look at. The detail isn't there, but if you think about the science and what's going on, I find them fascinating. Another grouping of galaxies. You can see different distortions occurring to the galaxies due to the gravitational interactions. And right to the end, Stephan's quintet, almost 300 million light years away. Back about a century ago, Stephan thought he had a quintet of galaxies, 1, 2, 3, 4, 5. But now we know that this one's only about 40 million light years away. It just happened to be in the field of view. However, this one has about the same redshift, so really the quintet goes like that. Just interestingly, this also was imaged by the Hubble and the James Webb Space Telescope. Wonder how the images compare. There's Starbase 13. There's the Hubble. There's the James Webb. If you normalize it to cost, now I realize that, of course, these really do science, and this happened to be just an image where they kind of overlapped in their abilities, but it was kind of fun to compare. And that wraps it up. Any other questions? Yes?
One question, how do you plan your evening? For example, there's, 7 hours of darkness. You have 42 10-minute windows. Do you plan where you're?
You absolutely have to plan ahead. You don't realize how destructive the moon is to this hobby, because you only get about 2 weeks a month of good viewing, and then if you can keep the clouds away, then anyway. So yeah, you have to plan ahead, and you catch as catch can. But luckily, you can take a little here and a little there and add them together, and ultimately you get it done. Okay. Any other questions? Well, thank you very much. It's been fun.